Alright guys, so in this video I'm going to talk about how we are able to identify objects, okay? You know, if you ever looked at a tree and wondered how you're able to identify that that's a tree, right? Or you look at a beach, you want to know how you're able to identify a beach. It's kind of a confusing problem because, you know, you look at a beach and it's like, you can't really define it, right? You can't you can only incessantly describe the beach, right? You can only you'll never be able to come up with enough criteria to put it into a sentence, right? Because how big are the sand grains, how many sand grains, how wide, what color, right? So it's very mysterious how we're able to look at this thing that we can't define and yet identify it. So, in the Gateian perspective, in Bill Gates' version of physics, light is not a wave, because wave is a verb. Light is a rope. So here's a rope. Obviously, it's like very, very far apart. Maybe we can make it a little bit. Sorry. Can make it a little bit thicker, maybe. Right, but you know, it's a rope, and frequency is simply link length, right? So with a higher quote-unquote frequency, you have wider gaps, but also less links per whatever distance we're talking about here. This is obviously a very tiny scale, so we'll call it a mini inch. We'll call this one mini inch. So for each mini inch, you have wider spaces between each of the threads, but also there's like more links, right? So that's what frequency is.
We have also C is equal to frequency times wavelength. Well, you can see that if you have a rope, right, and you torque it more, for the same amount of rope, I get more links, and each link is smaller. The wavelength is shorter at the expense of frequency. And now I unwind it. Now the links are longer, right? But what do I have? Well, I have fewer links. Now this is the equation of a rope. That is the equation of a rope. There's no other thing you can use to simulate that equation. And here, well, I see it show it in a little more detail. Okay? The longer you make the links, the fewer links you can fit within a given length of rope, and vice versa. C equals frequency times wavelength.
So let's make a new layer. Draw an eye. So here's an atom in the person's eye. And here is an atom in the source that they're looking at. Maybe it's a tree, maybe it's a rock, whatever. But the atom in the source will be connected to the atom in the eye, right? And so color is just sort of like the frequency of or the link length of the torsion that's happening. So light is basically just like torsion. Now, because light is a rope, this means that there are a finite number of inputs. Okay, so it means that there can be only so many inputs in the atoms in your eyes. Okay. Now, what this means is that because there are a finite number of inputs, it essentially means that we have resolution. Okay, so the screen that I'm recording on is 1920 by 180, right? It's 180 vertically, and it's 1920 this way. Imagine like a display that's like 30 million by 80 million, and it's sort of shaped in a sort of spherical way, right? And there's sort of like two of these there's two of these inputs, and they kind of get like patched together, right? Right, but you don't really see like the bridge of your nose, for example. It's just sort of patched together. So you have a finite number of inputs, you have resolution. What this means is essentially that the images, the objects that you look at are broken up into little pixels. So you see how there's a range of tone, but it's also broken up, right? It's broken up into little pieces. So altogether, it looks smooth, but up close, it's chunky, right? And basically what I'm arguing is that we identify objects the same way that a machine learning algorithm identifies objects, okay? Machine learning algorithm has a picture, and the picture is made up of little pixels, and it basically just assigns numerical values per the cue, and per like relation to other pixels, right? So if you have like a green pixel next to another like greenish pixel, that will mean something different than like if it's next to like a blue pixel or a gray pixel, for example. And so it's basically just like pattern recognition. But the key that I just want to give, that I want to offer here is it's resolution that allows us to identify objects. We kind of have this idea that like you look at an object and it's like it's a solid piece. It's registered in our brain as some sort of like solid piece. And what I'm arguing is that no, it's actually broken up. It's actually pixelated. So that is how we identify objects. Thank you guys and have a nice day.